Okay, so I may have, or some of you may have seen me before. I was here earlier. My name's Erin LeDell. I'm a statistician and machine learning scientist at H2O AI. And this talk is going to be about ensembling and sort of specifically about the type of ensembles where you take a bunch of different models and combine them together. So the first part of the talk, I'm going to have some slides, and then we're going to move over to some code. And actually, I'll maybe right now just show you where that code is if you want to get a head start. So you probably can't see this URL, but that's learn.h2o.ai, which is where all of our H2O World training from today is. And so this is the one we'll follow. And sort of the first half of this is sort of a text summary of what I have in my slides. And then the code part that I'm going to go through is starting here. So where I specifically talk about the H2O ensemble implementation. Okay, so let me pull back my slides. Okay, so the first slide is just what is ensemble learning? So that's kind of a generic term, and it's used to describe a lot of different things. So in general, it just means combining a bunch of different learners together to achieve a better performance than you would from a single learner. So that's a generic definition for a generic term. So let's talk about some different types of ensembles. So ones that you're maybe more familiar with are bagging and boosting. So bagging is essentially like a random forest is an example of bagging. So bagging, you usually average models together. And what that does is usually the models that you average together have high variance. So when you average them together, it reduces the variance and produces a better model. So yeah, random forest is probably the most popular example of that. And the next subset of ensemble methods is called boosting. So that's a different type of method. So it's an iterative method where you sort of train one iteration of it and see where you did poorly, and then overcorrect on the examples that you did poorly by reweighting them, and then you keep doing that and keep doing that. And so you sort of concentrate on the examples that are hard. But one of the consequences of that is that if you have a lot of outliers in your data or noisy data, it might start to get stuck on some of those outliers. And so that can be an issue, although typically the GBM is still one of the best methods. So a reason why people like it is that it's pretty flexible. And if you have a particular loss function that you're interested in that represents your situation well, you can use it with boosting, and it's typically still pretty powerful. All right, and so the last subset of ensemble methods that I'm going to talk about is stacking, and that's what basically the rest of this presentation will be about. So stacking is a name for ensembling a diverse group of strong learners. So the first two generally focus on ensembling things like decision trees, which are considered to be weak learners with high variance. So what differentiates stacking from some of these other methods is that you actually use a second step of machine learning to learn what the optimal combination of the learners is. So I know that's a lot of the word learn in one sentence, but basically you're doing machine learning on the machine learning and using the machine learning to tell you what the best combination is. And so it's a pretty hands-off method, and that's one reason that people like it. So I'm just going to give you a little bit of a history of stacking, because I think some people think when they hear the word stacking, they think, I don't know if I've heard of that before, or what is that? It might be something that you've already known, maybe by a different name, or maybe you just knew about the method but didn't know that it was called stacking, because it's had kind of a long history and had a lot of different names associated with it. So it started out in 1992 with a paper called Stack Generalization. So David Wolpert is the guy who is famous for the no free lunch theorems. So his if you're familiar with that concept, basically it's that no single algorithm is going to always be the best. So it kind of shows that that was his thinking when he came up with this. So he was the first person that presented the algorithm. And so he was a neural network guy, and so he blended neural networks together. So then a few years later, Leo Breiman, who's the inventor of random forest, came up with a paper called Stacked Regressions. And so he sort of changed a few things about the algorithm and did a lot of empirical study of this algorithm to find out that if you use cross-validation to generate this, I'll go on to explain further what this level 1 data is, but basically it's the data that you feed into the second machine learning algorithm. So he came up with that idea to use k-fold cross-validation rather than leave one out, which is what Wolpert was using. And so he also kind of focused on blending the same type of algorithms together. So he blended neural networks together with different basically model parameters. The same with GLMs. He would take a GLM and do different sort of feature subsets on that and stuff like that. And so he didn't play around too much with combining them together, but he was aware that that could be something that you would try and talked about it, but he just didn't go too far into it. So then, people were using these things, but they were essentially considered to be a black box. Nobody knew why they worked, and there was basically no theory behind them. Until 2007, there was a paper called The Superlearner, and that is by Mark Vanderlaan at UC Berkeley. So he provided the theory that proves that the superlearner, or this stacked regression construct, is what we would say is asymptotically optimal. So that basically just means that as you go to infinity, it's basically indistinguishable from the oracle, or just knowing the true function. And so the first R implementation of stacking, at least that I'm aware of, was in 2010. There's an R package called Superlearner. And there's one other implementation that I'm aware of that was in the Weka software. And so that's actually been around for a little while. I don't know exactly what year that was written, but that's pretty much the only other implementation that I'm aware of. Now there is a package called Caret, if you're an R person, there's a new sort of add-on package for that that's called Caret Ensemble. And I've looked at that, and I think the last time that I looked at it, they were doing something a little bit different than exactly what stacking is. So instead of using cross-validation, they did like a test and train holdout set. So anyway, so this is sort of a history of stacking. So it's been around, and it's sort of pervasive, but not as popular as some of the other algorithms that you hear about. Okay, so I'm going to explain the algorithm. It's actually quite simple. So what you do is, you have some set of base learners, and maybe a random forest, a GLM, an SVM, or whatever. And they all have, and you actually can have multiple versions of things. So you could have a deep neural net with one certain architecture, another deep neural net with a different architecture, and you kind of just have them all together. So the first step is that so if you're not really interested in the math, you can kind of tune out for the next 3 minutes or so and then catch up with me. But basically how it works is you use cross-validation on each of your base learners. So what happens when you do that is that you break up the data into k-folds, and you do k-fold cross-validation, and then you end up with a vector of, let's say you started out with n data points, you'll get a vector of n predicted values, and they've been cross-validated. So each learner produces these columns that are n long, and so you can actually, so you have this basically, here I'll show you the next picture, which will kind of describe what I'm talking about here. So basically that P1 through PL, those are just the cross-validated predicted values, and you kind of just squish them together into a new matrix. and then we'll call that Z, and then you do another round of machine learning. So that now becomes the, kind of your X matrix or your design matrix, and then you fit what's called a meta-learner, and the meta-learner is just any old algorithm. There's nothing special about it. It's just another algorithm, and what it does is it tells you, once you have the predicted values from each of your learners, it tells you how to combine them together to get the final predicted value, so in the optimal way. So the data that goes into the meta-learner is sometimes called the level 1 data, whereas the original data set is called the level 0 data. That's just some terminology. So anyway, that's the algorithm. It's quite simple, and there's not much to it. So one thing I like to think about is, so when we're doing super learning or stacking, you're doing all this model training, but and so some people think, well, that's just, that's a lot of work. I don't want to wait forever for all these models to finish. But essentially what you're doing in a normal machine learning or data processing type of situation is that you're doing this anyway. You're doing maybe a grid search or a random search or just some, handful of models that you're testing out. You usually don't just take the first thing that you get. So you're using all this computing power and doing all this work, and then at the end you're just picking one model. So you kind of throw away all that work that you've done, or compute time that you've paid for on AWS or whatnot. So with Ensembles, you actually can make use of all this work that you've done. So yeah, there's not much overhead into ensembling them together. You're already doing all the work by cross-validating each of the models. So you're not really wasting anything. Okay, so now I'm going to talk a little bit about the H2O ensemble, which is the H2O implementation of superlearner. So this is sort of how I like to think about the superlearner. So there's all these different, powerful beings, and they each have their own unique skill set. And even, maybe some of them aren't that great, they all contribute something. And everyone has something unique to offer, even if it's not necessarily good on their own. So that's kind of how I think about it. So in the Ensemble package, we currently support regression and binary classification, and we'll be adding multi-class classification soon. So the H2O Ensemble package, I should mention, it's right now, so it's an R package. So all of the Ensemble code is actually written in R, but how that works is that the H2O R package is really just making a bunch of calls to the H2O cluster, which is actually doing all the work. So the plumbing of the Ensemble algorithm is just sort of organizing the training of all these different models and reorganizing the data afterwards. And so no data is ever pulled into R. So it doesn't matter really that it's written in R or not, basically. So you're not losing any performance by doing that. It makes it so that it's only available in R, which is why we're probably going to move it into Java so that it can more easily be accessible to our other APIs. But it should be relatively no overhead from that. So what are some of the reasons why you would want to use an ensemble? Well, one reason is when a single algorithm does not approximate the true prediction function well. So unless you have a truly linear relationship between your data and your outcome, or something else that can be approximated by one of the more simple algorithms, you're probably going to do better when you're sort of averaging over all the different types of algorithms. And another reason is it's pretty much the only way to win at Kaggle, as far as I can tell. So I'll show you a little bit about this. So here's just one of the leaderboards for this Give Me Credit score. So this score here is actually the AUC. And if you'll look, you'll see the top, several decimal places is what it takes to actually win. So yeah, so 4 decimal places in, if you got a little bit more, you might win over being second place or even third place. So every little bit counts. And so that's why people use ensembles. They don't use them because they take less time to train. They use them because the goal is accuracy. So if that is your goal, this is the way to get there. So from the same competition, I just took a look at sort of what the first and second place teams said about how they won. So this person says, let's see. They applied an ensemble of 5 different methods: a regression random forest, classification random forest, feed-forward neural network with a single hidden layer, gradient regression tree boosting algorithm, blah, blah, blah. So basically, those are all actually in H2O. So you could probably replicate what this guy did. So that was the person who won first. Then the second place, so he used 15 models, GBMs, different versions of GBMs, random forest, balanced random forest. So you'll see people doing multiple versions of the same algorithm. So one thing that might be useful in an ensemble, so in H2O now that we have the ability to do to randomly select just a portion of the features in the GBM, you could do one version of the GBM where you selected maybe 50% of the features, and another one where you selected 90%, and so the goal is really to get diversity, and you're not going to get diversity by adding the best model from each class in there and like trying to do it that way. You're going to just throw in things that you think are bad, and you throw in things that you think are good, and sort of anything in between. Okay, so this is just where the package is on GitHub. So if you have your USB stick, the package is on there as well. So you can install it from there, or you can go to the H2O GitHub, and it's in the H2OR folder /ensemble. And if you scroll down, which you can't do on this slide, but if you scroll down, you'll just see the command to install it directly from GitHub using DevTools. And that's, if you have the USB stick, you can do that. Otherwise, the DevTools GitHub way is probably best. Okay, so I'm just going to, before we get into the code, just sort of demonstrate a little bit at a high level what we're going to do. So the library is called H2O Ensemble. So what we need to do is we need to set up what we call the base learner library. So just pick in this example, I have 3 different learners. So this is a pretty simple example. So I have 2 different deep neural nets and 1 random forest. And what you see here is those are just strings, but the strings are representing the name of a function, and each of those functions is a specific random forest with a certain set of parameters. So I could, I'll show you in the code, we'll go through how to customize each one. So I have all the algorithms that are supported in H2O, and I have all the default parameters, and so if you want to just do nothing, you can just use all the defaults and put 1 of each in there and see how it goes, or you can start to customize them and change the parameters to get a little bit more diversity. And then I mentioned the meta learner is just another algorithm. It could be anything you want. However, GLMs seem to work pretty well. Well, I shouldn't say that. Not regular GLM. So if you were to use just a standard GLM, that it would actually work really poorly because the predictor columns are very highly correlated. So the GLM that is here is the H2O GLM, which by default has regularization, which will deal with some of the problems that you have when you have collinear predictors. So we have a family argument. So this is so that our GLM has the family argument. So there'd be binomial or Gaussian in this case. So that if you're an R user, you're probably familiar with that term. Okay, and then this is just the function. So it has the same interface as all the H2O functions with the X and the Y and the training frame. And then we have these just additional arguments, and there's a predict function as well that works how you would expect it to work. Okay, so here are the links to where the demo code is. And so you can either go to the GitHub page, or there's this learn.h2o.ai site, which is mirroring what is on the GitHub page. So, okay, so let me pull up. Okay, I'm going to have to make this bigger. Okay. All right, so there should be on your USB stick or wherever you found it a file called ensembles-stacking.r. So at the learn.h2o site, there's a page there that has a bunch of markdown on it. And so I just stripped out the R code from that markdown page. So that's why there's a bunch of comments here. So you can kind of ignore those comments and scroll down to where you want to start the code. So this is, if you don't have it on your machine yet, you might want to run this. So library DevTools, install GitHub. Otherwise, you can just go ahead and load the package. So let me make this one bigger. And I will pull this over here. OK. So load the package. We're going to start an H2O cluster. OK, actually, I'm going to kill that one because it's been on all day. OK, so start again. OK, so we're starting up a new H2O cluster. I typically always use number of threads equals -1, which means use all the clusters. So I'm just running this on my laptop, so it'll be 8 cores. This will remove anything that's there. OK, so the one thing, or actually there's 2 things in this file that you'll have to do. One of them is if you actually want to import the data and have these functions work, you're going to have to set your working directory to wherever you have this folder on your local machine. So I'll just wait a second in case anyone wants to do that. So do that. OK, so then now I should be able to, those relative paths should work. So I'm uploading just 2 CSV files. One is the training set, one is the test set. So you could also just upload one set and then split it using the H2O split frame function. But I have 2 separate data sets here. And so what this data set is it's called it's a subset of the Higgs data set, which is a numeric binary outcome data set that I like to use to test things because it's nice and clean, and I've been using it for a while, and it's kind of an interesting problem. So this is just a 10,000 row subset because, as I mentioned, it does actually take a while to train all the algorithms, so we didn't want to have a billion rows or anything like that. So the first column, C1, is where the response is. And so I'm going to say X is all the columns that are not Y. And so then, because we're doing binary classification, we want to convert the outcome to a factor or enum type. So if you don't do this, then some of the algorithms will complain if you try to do the binomial family on that. So you can also specify the types as you import the file, but if it's just one thing, like a one outcome, usually I just do it in the code like this. All right. So this is the part where we're going to specify the base learners and the meta learner. So these are actually the 2 defaults that I have for learner and meta learner. So this is just the reason why it's called h2o.glm.wrapper instead of h2o.glm is because I had to make sure that all of the input arguments matched up. And at the time when I was writing this, there was a little bit of overlap that made it, so some of them have distribution instead of family, and so we're converging on that. But at this point, the GLM still uses family, and the other ones still use distribution. So these are just little wrapper functions around that make that, that sort of unify the interface a little bit more between the four different functions. So this ensemble will have a GLM, a random forest, a GBM, and a deep neural net, and we'll use the GLM for the meta learner. OK. All right, so the next thing is we'll run this code. And so this one argument here, CV control, this just has to do with how many, so remember when I was talking about the step where you do the cross-validation to create that level 1 data? So this is just specifying that I want to do 5-fold cross-validation. That's the default. But if you increase that number, you will probably get better results. So if you did 10-fold cross-validation, it would be better, and it would just take twice as long. So I think 5 is kind of like a good midpoint to start out with. So what this is doing is it's actually doing 5-fold cross-validation on each of those learners and then training an extra learner at the end that's on the full data. So that's generally what happens if you use the n-folds argument on any of these algorithms. So we'll wait for that to finish. So this is the part that actually takes time. The meta-learning step you'll see is pretty fast in comparison, so that's done. All right, so now we have an ensemble fit. And so what that actually consists of is these 4 fits that we've trained here and a meta fit, which that's sort of like a word that I invented, but, well, I didn't invent it, but that's what I call that level of basically the fit for the meta learner. All right, so now if we have a test data set and we want to make new predictions, we just use the predict function. And maybe I'll just show you quickly what that looks like. So for the ensemble, it's a list, and there's 2 H2O frames in there. So remember, none of this is in memory. These are all references to or in our memory. These are all references to the H2O frames that exist on my miniature cluster on my laptop. So pred is actually the actual ensemble predictions. So, and base pred is the predictions from each of the base learners. So it's kind of useful to know, if you're using this type of thing, and especially if you're using it on small data, if you want to always ensure that you're making a good choice by using an ensemble. So maybe, you put in 40 different learners and you only got like this much performance gain. Maybe this is one way to find out that you don't want to use an ensemble. So what we'll do next is we'll generate some performance metrics. So I'm going to pull out here I'll just show you what this pred thing looks like. So this is just like what any input of a binomial prediction function in H2O looks like. So it'll give you the actual prediction if you want it, 0 or 1, based on just a default threshold. And then the P0 and P1. So P1 is actually the probability that we want. So that's the probability that y equals 1 here. So I'm just going to pull that out. That's why it says this. Oh, and so the other thing I should mention is, so right now so in the other H2O algorithms, we basically pre-calculate all the metrics for you, and we do that in Java. So that's not implemented yet in H2O Ensemble. So if I want to measure the performance, I'm going to probably do that in R. So that will change, but this is how we do it now. So I'm pulling out the predictions, and I'm making another object called labels, and then I'm going to use a function to calculate the AUC. So I didn't mention this, but there's another package that my code uses. It's also on the USB stick or CRAN if you want to download it. So it's just called CVAUC, and it's just a utility function that I'm using here. This package actually does more than just calculate AUC, but I'm just going to use the AUC function. Okay, so the first thing I want to point out is that this number here is different than the one here. So this is just, I put the results from when I ran it once, and to sort of emphasize that this, at least for this first example, this was not a reproducible function. So the reason for that is twofold. One, the deep learner is never reproducible on multiple cores, and that has to do with basically just how the deep neural net is implemented, and it's the reason that it's really fast, but it makes it not reproducible. So if you ever have a deep neural net in here, that can change from run to run. And the second reason is, by default, the random forest doesn't set a seed. So that's also going to change from time to time. So if we look down here, so this function here is, I'm just going to find out what the performance based on AUC of the individual learners is. So you'll actually notice that between these two things, the GLM is the same as now, because that doesn't change. Random forest is slightly different. GBM did not change. And deep learning actually went down a lot this time. So what we'll do next is, I guess, make a note, first of all, of the performance gain that we're getting. So right here, 0.787 is the ensemble AUC. And so the best that we can do from an individual learner here is the GBM, which is consistent with what I usually see, is 0.781. So again, that's not a huge gain on a data set of just 10,000 rows, but it's certainly enough to go up a couple hundred slots on Kaggle. OK. So I said I would tell you how to make your own customized wrappers. So here's a bunch of I just put a bunch of them in there that you can play around with. Here's a bunch of different GLMs where I've changed the alpha parameter. So that's one way that's probably, I mean, there's a lot of other ways that you can modify GLM, but I'm trying to keep it a little bit simple here. So random forest, here's 4 different versions of that where I do different things with sample rate, one where I'm doing balanced classes, and then GBM, I am doing a whole bunch of things. Here's the thing that I mentioned with the column sample rate. That actually works pretty well. So you would probably want to try that. Here's making a little bit more shallow trees. So I think max depth equals 5 is the default. And then here's a bunch of different deep neural nets with different architectures and stuff like that. So what we're going to do is just take a few of these and put them into our new library. And we'll keep the same meta learner as before. And so now I'll train again. Oops. I have to actually put these into memory. And then run this. OK, so this will take a little bit longer because we have more to do. So while that's happening, I should explain. So what you see here is it's doing the learning of each of the algorithms in a serial fashion, so one after the other. However, each of the algorithms themselves are completely utilizing the whole cluster as much as possible. So that is something that we might look at in the future of how to sort of mess around with that to see if, where the trade-offs are in terms of, is it better to just spread out the algorithm across the full cluster and then just do that every time? Or is it better to do half of the cluster and then do 2 at once? Or there's all sorts of variations that could be explored. But this is what we have right now, and I think it's certainly on relatively small clusters, maybe less than 50 cores. This is probably the most efficient way to do that. So let's see. This is going to take a few minutes, so I see I have 1 minute left to QA. So what I'll do is I'll actually, while that's running, I'll just sort of walk through the rest of the code so we can finish in time. So basically, I would do the same thing once it's finished. I would calculate the AUC for the ensemble, and now I get 0.79. So before we got, I don't know, 0.788. So we're doing better. We have a more diverse library now. And this is the performance from the last run that I did. So The highest that we got, I think, was 0.783. So now we're 0.79 versus 0.783. So now maybe you start to think, maybe it's starting to be worth doing this extra work. All right, so one thing that you might think, and I've heard people suggest this before, is, well, why don't you run an ensemble and see what the best learners are, and then take those ones and then ensemble those together, because that's going to be better. That's actually not the case. It sometimes could be the case. But the next example, which probably won't have time to run live, what I'll do is I'll take in each of these categories, so I'll take the best, actually, let's see. Yeah, I'll take the more strong learners. So the random forests and the GBMs are doing, on this data set, better, actually much better than the GLM and the deep neural net. So what if we were to just take those and ensemble them together? You would think that we would have a better learner, maybe this GLM is bringing us down. It's not helping us at all. 0.68 is pretty bad compared to 0.78. So what I did was I removed the deep learners and the GLMs, and then I retrained. And actually, the ensemble prediction went down. So this kind of shows, at least the point that I'm trying to make, is that maybe your intuition about ensembles might not be quite accurate. So that it actually helps when there's worse learners in there if they are different types of algorithms. So if, just because the GLM is such a structurally different algorithm than the other ones, and same with deep neural nets, it's just able to use pieces of that and approximate the true prediction function much better than just using these two tree-based methods, even though they do better on their own. So that is the lesson to take home. So still going, it's almost done, but looks like it's time for QA, so I will just let that go, and we'll open up for questions.
How much of this in the real world, when you're seeing people use this, is this really just used as data dredging, just going to throw another method at it, another method, versus someone sitting down and really trying to figure out why didn't this model work? And okay, now this one has a lot of outliers, so now I'm going to use an algorithm that's more robust to outliers. Methodically going through it versus just throwing everything at it, running it, go home and see what happens in the morning.
Okay, so I think there's two ways to answer that. One is that we've seen that even if you put in bad learners into the ensemble, it helps the whole ensemble altogether. So if your goal is to find just one algorithm that's going to be the winner, and you just want to, let's say, go to production with one algorithm, then that's what you should do. You should take the time and try to figure out, on this data set, why does, random forest work really well, and try to really figure out what's going on there and do some real data science. But if your goal is just to get the best prediction, then you probably will have a better chance just throwing in a whole bunch of stuff. I mean, it helps if you throw in things that are actually strong as well. I guess the point I should make is you should do the work to find out which ones are good and put them in there, but don't leave out the bad ones. So throw in some bad ones if they have a different algorithm class. So I guess if random forest is your best algorithm and you have a bunch of not as good random forests, that's not going to help very much. But if you have a not as good GLM, that is going to help. So that's sort of the takeaway.
So,
right here.
So in your meta learner, you always had a GLM as your meta learner. So is that rule of thumb that the meta learner is always GLM?
I heard part of the question. You're asking about the meta learner being a GLM?
Is it always true that the meta learner is GLM?
No, but I think that in my experience, so actually I should say that the most popular meta-learner to use is a form of GLM called NNLS, non-negative least squares. At least historically, that's what a lot of the older papers have used. And there's some theory behind restricting the, if you're using a GLM, each of the coefficients represents a weight. So restricting them to be non-negative actually helps. But in the H2O ensemble, you can, I've had the best luck using GLM. And sometimes deep learning, but hardly ever GBM or random forest so far.
Are there any heuristics on the number of models?
Heuristics on the number of models. I guess it depends on, your time situation and how anxious you are to get an answer. I think I like to start with at least 4, one from each. I mean, in the H2O ensemble, we have 4 different algorithms to choose from, so I would start there. And then, I've seen people use hundreds, but you have to have some patience for waiting around for that to train. So one thing that I'll be adding to this package is the ability to kind of like hodgepodge models together. So if you train some over here and you train some over here and you want to actually combine them later, you don't have to like retrain them all. So that'll be like some sort of utility function that would do that.
So with hundreds of models, is there a big improvement or just tiny compared to maybe a dozen models?
I would say that there's diminishing returns. So, yeah.
I have a kind of a basic question. Say you have a set of classifiers that have high precision but poor recall, and then you have another set of classifiers that have other way around, high recall but poor precision. And then you want to kind of boost both. Does stacking make sense in this context, or?
I think it does. I haven't specifically done that with that in mind, but that would be a sensible thing to do, I think.
So even if the algorithms, the underlying algorithms are like the same, because a lot of times, the same algorithm, there's a knob that controls the precision and recall, right? So say you have a set of algorithms, the same algorithm, but with the knobs set to high recall, and then
yeah, I think that's actually a good technique, and I've seen, at least on Kaggle, people have used different subsets of columns with the same learner. So they use a GBM with, maybe the first half of the columns and a GBM with the second half, and sort of, adding variability to the model that way. That's one way to do it. So just changing the data itself. Or if you have knobs that you can tune enough to sort of get something different, then that would be another way to do it. There's a question over here. Yeah. Do you want to get the, oh, sorry, one
yeah, is there any theory behind or some sort of orthogonality between families of things that benefit the most from ensembling? You said you've got better luck ensembling weak learners, so to speak, or learners that are very different from each other. Is there any theory behind what are 2 things that are the most different that will benefit from it? And if I get a supplementary question, does recursion on ensembling, meaning sub-ensembling and then ensembling the results of the 2 subsets, lead pretty much to the same as having ensemble across everything the first time around? Thank you.
That's a good question. So I think what you're asking is if, let's say you had a bunch of random forests or something, and you ensemble them maybe together, and, okay.
So my second question was, if I was going to ensemble between, n models, 8, would I get the same, had I done it the same first time around across the 8, or pick a random 4, ensemble those, pick a random 4, ensemble those, and then
oh, I see.
iterate?
Well, there's not really a way to combine those 2 groups together in the way that they would be equal to if you had just started with 8. So you would have 2, super learners that were together, and maybe you could then average the result or something. That's actually something you might want to try, because once it gets to the ensemble level, the prediction should be pretty good. So if you average them together, it wouldn't be that bad. But actually, I would just choose whichever one is better.
Okay.
Probably. And then, yeah.
Generally, in mathematics, we have a very precise way to make choices, because theories are built from axioms and are very well defined. Okay. Instead, here we have the possibility from the observer to make a choice, and the choice is the best fit. But are we sure that the best result is really the best result? Because each algorithm can be part wrong, part true, and we're not absolutely sure that in that specific cases, what algorithm is really the best, okay? Because there is no theory that tell to us how to make the choice.
Yeah. Okay. So the question is there a theory that says that this algorithm is better than that one, or how do you know it's really the best? And I guess the answer is, at least according to the theory of stacking, that, I mean, so let me separate two things. One is, as you're mentioning, the user is choosing what to put in the ensemble. So that's, how do you know if your choice of models is the best? And then the other is sort of just looking at from a theoretical standpoint. You say, if I were to put in like all the models, this would be the best. The superlearner finds the best combination of these models, and that's the best thing that you could ever possibly get. So it's a matter of you being able to replicate what the theory is trying to do. So if you could just put in every combination of everything ever, that's sort of guaranteeing that you would have the best model. But in practice, you have to make some choice about what you're going to put in there. So yeah, you're not going to have the best theoretical model possible. It would be better if you put in one more model, or if you put in another model or another one. So you can kind of just keep going, and you're sort of on the right track. But so you're headed in the right direction. So if you have enough computing power, you could, I mean, you can't get to infinity, but that's.
So just a quick announcement. Right now, between 3:45 and 4 o'clock is a quick coffee break. So there's espresso and coffee and all other sorts of caffeinated refreshments available outside. Feel free to hang out here and continue asking questions if Erin is willing to keep answering them. But just this is a break time. So feel free to move around if you have to.
Is there any reason why we couldn't do an ensemble model of ensemble models? Theoretically?
No, you should.
Okay.
Okay. Oh, yeah.
Hi.
Oh, wait.
So here.
So how are the?
Oh, hi.
Hi. So my next question is, so when you do ensemble models, can H2O output some objects, and we can do summation or multiply or like this? So.
So you want to do like a summation of different models? Is that what you're saying?
Yes, like the output some objects, and then we can do some calculations based on objects.
I'm not sure exactly I understand what you're saying. So you want to take the output from the base models and do something?
Yes.
So if you wanted to do something customized, then you could write your own meta-learner function that would do whatever you wanted it to do.
So H2O does provide that, right? Okay. Thank you.
How was different the base model and the final model stored? I mean, as far as prediction goes, can we do predictions?
Yes, it can. So right now, the way that it's stored is if there's a function called H2O.save_ensemble. And what that will do is save all the base models and the meta-learner model as using the H2O.save model function. So you're saving these binary models to disk, and then you just save them basically in a folder, in a collection. And then there's a H2O.load ensemble, which will then pull them all back together and reconstitute them in the model form. But when we move this to Java, that will change, I think. We'll have a different format for doing that. So all of the H2O models now, you can output a POJO or a Java code that will you can take and put on a machine somewhere. So what I think we're going to do is have all the individual POJOs and then like another POJO that tells you how to combine the other POJOs together type of thing. So, we would be looking for feedback if you have any recommendations or any, when you're using this, if it works for you in your production environment or it doesn't, you could let us know. But that's, I think, what our plan is.
So basically for production, prediction, you have to go through the base model, then the base model goes towards the final model to figure out the result. So
yeah, so if you're, what you can do to make this fast is you can make all the predictions from the base model at the same time. And then you feed those predictions into the metafit, and that gives you the final prediction. So instead of doing it in one shot, you do it in two shots. But you should be able to parallelize the base learner predictions.
Another question related is, all the base model have to have a same set of feature, or we can take like 80% of feature?
You can let me think, if that's implemented right now. Yeah, so you could write these little wrapper functions that I have. Within the wrapper function, you could just say, oh, I only want to keep like a certain subset of the features before it passes that on to the internal stuff. So right now it's set up so that there's an X that you specify in H2O.ensemble, and that will be your full, whatever your set of features is. And by default, it will just pass. It will have all the base models and the meta learner, or sorry, just the base models use those specific features. But if you were to write wrapper functions for the base models that just would change that X value, then you could do that. And maybe that's something that I would add as a
Sure, thank
in
you.
a more
Last question is, I know the feature, you can take it like 80% of feature, another 80% of feature for two base. How about data? Do I have to use all the data to train for each base ones, base learner?
So right now you do, but there is another version of this algorithm that's called Subsemble, and there's an R package that I've written that does, that's a particular version of that where it partitions the data in a certain way, and then you make like little mini models and ensemble them all together. But we're definitely going to add something so that you can both change the feature set and the training set in a way that you have control over for each of the base models. Because you should, it's harder to do, so the reason behind Subsemble is there's a trick in that you can get all the cross-validated predictions the way that it works, so that if you, in one of the base models, if you were to cross-validate it and you only had half the rows, then you would only have half the predictions as the other ones. So now you have like, n divided by 2 column and then these n columns, and then you can't really train a new model unless you subset everything to the shortest one. So the way that the subsemble algorithm works is there's a trick that it does with cross-validation so that you actually get the whole n-sized level 1 data back, and then you can train on that. So yeah, but you could send me an email if you want to chat about it. Mm-hmm.
Should you be providing a Python API to the Ensemble function?
We don't right now, but we will soon.
It's a work in progress.
Yeah.
Last question?
Thank you very much, Erin.
Thanks.